Okay, so good morning. Welcome all for this session 5, that is session 9 of day 5. I'll be discussing on the fluid mechanics applications using MATLAB. What I'll be covering today will be a little bit of fluid statics. My content, my presentation would be, so I'll be covering on fluid statics and the fluid kinematics. I'm not going to full touch upon the fluid dynamics, because fluid dynamics will lead to what is called as CFD, as most of you want to learn how to at least try using what you have learned, like plotting, contour, all those things. So if you're able to learn fluid kinetics, you can easily migrate to CFD. I think you'll be able to write your own codes and you can go ahead. See, when you speak of fluid statics, what I'll be discussing, I'll be taking up one simple example problem. Say, for example, a patient admitted in, let us take on practical example, like a patient admitted in hospital and he is taking some IV fluid, and the IV fluid is from a particular bottle, and what should be the height of the bottle, so that we can write a code and we can do that using the Pascal's law. And let's look at some examples with respect to manometers. That's one thing. And coming to the fluid statics, so what we will be doing is, we'll be discussing on the path line, the streamline, and if possible, streak line. That's one thing. And the second one will be, let's look at the one example of acceleration of the fluid through nozzle. I think I will stick to this particular 4 to 5 examples. And what I'll be doing is, I'll be going through the problem statement, and in that I'm going to already have attached the MATLAB code which people can run. So when I switch over to demo session, whatever the code I am running, I will just copy and paste in the chat box so people can try. Okay. So coming to fluid statics. Let us discuss on few fundamentals, then we'll move. So when we come to fluid statics, the first and the foremost thing what we come across is actually measurement of absolute pressure. So if suppose I have a datum something like this, so this is my datum and I want to measure the absolute pressure. So let's, for example, this is my absolute pressure, this is your datum. So I have another side, and I want where is my atmospheric pressure. Say, for example, if this is my atmospheric pressure, your absolute pressure, whatever you are going to measure, this is the one, will be equal to, this will be your the gauge pressure, and this will be your atmospheric pressure. Suppose the same thing, if it is vacuum, so this will be your atmospheric, and I'll be having my absolute somewhere here. Absolute will be here, and so this will be automatically become vacuum, P vacuum, and this will be your absolute pressure, and this is your atmospheric pressure. So using this, actually, what are the equation what we have? We can write P absolute is equal to, right, P atmospheric plus P gauge. Okay, P absolute is equal to P atmospheric. Suppose if it is vacuum, P absolute will be equal to P atmospheric minus P gauge will be P vacuum, which already we have studied. This particular thing we know. Okay. Now, let me move to intravenous infusion. So as I raise the bottle, so I'll be able to get that particular pressure. So that particular absolute pressure, if it is something like 12 or 13 kilopascals, if I try to rise it, actually the number may increase. It may become 18 or 20 depending upon your atmospheric pressure. Now there are two cases. So look at one case. It is observed that the fluid and the blood pressure balances each other when the bottle is at 1.2 meters. So it's an incompressible condition. So it's an incompressible condition. That's where your the pressure is given. So it is something like the absolute is equal to your rho GH. This is the problem what we have. So now, depending upon the density of the IV fluid, such as for example, if it is a water, so around 1000 will be there. So I want to add something to that, some injection or something I want to add. So the density is slightly going to increase. So now when your G is there. Now this height depends on where we are going to see. You can see this particular thing. Now usually this from the base, this will be around 1 to 2 feet depending upon the bed height actually. 1 to 2 feet, 1 or 2 or 3, whatever it may be. Now from the bed height, where the patient is lying, to where you are supposed to see this particular thing, where you are supposed to put your maybe the point to which it's going to flow. So this particular height is what we are looking at. So now the condition, maybe the problem, I can write my own code and tell that. So the H can be one of the variable. H can be one of the variable. So depending upon this H value, I can calculate my absolute pressure. Or if for a given absolute pressure, because here I am taking my atmospheric pressure as the datum. So depending upon that particular condition, I can calculate. So either I can calculate the height. So here height is given, and if height I can calculate depending upon the absolute pressure. Now the one more biggest variable what we have here is for both the things is my density of the IV fluid. So I can fix a range, if possible I can fix a range, or you can put that as an input variable. So maybe 1000 or 990 or 990, whatever it is. Okay. Now I've written the code. Let's look at this particular code where I'm trying to input rho, that is rho as a density, input the value of the density of the IV fluid. So I'm inputting the rho value and input the value of the height which is placed in the this is the IV fluid. So this is your height. I'm inputting rho and H. So anyhow, G is a constant. G is a constant which I can define, or I can, if you want, I can input that. Now, if I want to run the program for only one value of H, I can define it. Or if I want to check it for n number of things, I can put it as an input. Now, what I'm trying to calculate, I'm trying to calculate the absolute pressure using your Pascal stuff is equal to rho GH, and either I can display or I can get the print. Okay, first thing. Maybe if I take the second case where I'm trying to input the absolute pressure. I'm trying to input the absolute pressure, or you can write the input command, or you can tell the input the value of the absolute pressure in kilopascals or pascals, whatever it may be, I can put it. Then I can calculate the H. So what is the formula? H will be your P by rho into G, where rho is the input, already we have, G is there, so I can calculate the H and I can get the display. Okay, this is a simple question. Most of the fluid stats to begin with, so to understand the Pascal's law, because the pressure at a given point remain same. That is, the fluid is under stationary condition. If P is equal to rho gh or P is equal to omega h, what we have studied, that we can apply this particular problem. So we can have such n number of problems we can have. Say for example, fluid in a manometer, or maybe you have n number of fluids in a manometer. Try to measure the pressure across it. These are some of the examples what we come across. Okay. This is about the code, and if you run it based upon the input values. So when I go for the maybe when I take it to the MATLAB, I'll run this code and I'll show the values. So this is the code. Okay. Now let us look at the second example. It's on the manometer. Okay. Now I have a manometer. The manometer is used to measure the pressure of a gas in a tank. Okay, that means this is my tank, and I want to measure the pressure of it. And depending upon, see, look at this. You know, specific gravity is one of the variables. So 0.85, or it can be any number. So depending upon the type of the fluid, the specific gravity I can vary. We know that specific gravity, and we have the standard density of any fluid. So water will be the standard fluid what we have. Now, the column height, look at this particular height can be one of the variables or for this particular thing. So h can be one of the variables, which is around 55 centimeters or 0.55 meters. So it is shown in the figure. Now, if what will be my local atmospheric pressure? So it can be 101 kilopascals or it can be 90 kilopascals. So as I go up and above your particular sea level, so this particular atmosphere pressure keeps coming down. So roughly I can take this particular problem, they given 96, so I can keep that as a variable. So when I write in the code, so determine the absolute pressure in the tank within the tank. So what I'm supposed to do actually, I need to write this particular balance the equation. So what are the equation? I'm supposed to use it, which already we know when I'm using the manometer. Okay. So what will be the equation? So if at any given point I want to calculate the density of the given fluid, so it is specific gravity of that particular fluid, okay, given fluid into density of the standard fluid, which is your water. So if it is 0.85 into 1000, so I'll be getting 850 kg per meter cube. Okay. Now, how to calculate this particular the pressure from this actually? So the pressure at the given tank, whatever the tank is equal to, so P atmospheric, fine, plus your rho into G into H of that particular fluid. Okay, rho into G into that particular. So if this is one input variable I can give, so it is now in this problem it is given as 96 kilopascals. Now rho, if I track rho of the fluid, I'm going to calculate and I'm going to put it over here, and depending on H is given the numerical, H is also one of the variable. I can easily calculate and that can be your way. Okay. So what will be the gauge pressure? Say for example, if I want to get the gauge pressure, it is P absolute minus P atmosphere. That is only your rho GH. If I do, I'll be getting my gauge pressure. Suppose if I try to calculate it, actually 96 plus 850 into 9.81 into 0.55, so roughly I may get around 100 kilopascals. So 100 minus 96, I may get around 4 kilopascals will be your gauge pressure. So I can write a simple program where these are some of the parameters. So why I'm teaching this particular, why I'm asking you people to do this actually. So most of us, we have been teaching this fluid mechanics. Okay, fluid mechanics we have been teaching. We can ask the students to, they'll be solving so many problems on the board. When we ask them to write some code actually, so when I try to vary the variable, so if my specific gravity is varied, so what is the impact of the specific gravity? What will happen to that particular? We can easily teach them. So I'm looking at the pedagogy point of it. Okay. So I've written a code actually, a simple code. Both of the codes are very simple. Okay. So now, so we have to be very careful when defining the variable. So this program is to measure the pressure in a manometer, a simple manometer, what I have taken. So yes, is my variable, that is specific gravity, and P atmospheric I'm defining. Okay, this is specific gravity and this is atmospheric pressure. Then H is one of the input. Height. What is the height with which the fluid is? So I'm trying to input that also, height. Then G is already given. Now I need to define what is my standard fluid. So for fluids, for water, I think we take water, and for gases we take air as a standard fluid. So we know that 1.18 for the air, and for water we take it as 1000. So I have calculated, and so I have found out the absolute pressure using the simple formula. So either I can print it or I can use the display format, and I can get the P value. So now, see here, when I'm trying to run the code, I will try to see to what decimals you want your output, whether it is rounded off to 4 decimals or rounded off to 1 decimal point. Those things will take care, depending upon the problem, what you want your output. So that can be taken when I'm trying to maybe write the code or run the code. I will show that what I'm trying to do from this. Now we'll move to the third problem. See, the third problem, the same methodology can be extended to your differential manometer, or as well as for your inverted differential manometer. So both, so I think with one problem I'm going to explain. You people can try in your fluid mechanics textbook either the regular differential manometer or inverted differential manometer. The methodology will be the same. Okay. Now look at this particular problem. The water in a tank is pressurized by air, and the pressure is measured by a multi-fluid manometer as shown in the figure. Okay. The tank is located on a mountain at an altitude of 1400 meters. Okay. Now look at this. Deliberately I have given this particular thing. This is from the Sentinel I have taken 10,000. So what will happen if this number is 1200 meters? If it is at 2800 meters, so my pressure is going to vary. Okay. So this particular thing, maybe I have some kind of a data handbook or something where, depending upon my altitude, I'll be able to get my atmospheric pressure as an input. Determine the pressure in the tank if H1, so this particular thing is equal to 0.1 meters, H2 is equal to 0.2 meters, sorry, H1 is 0.1 and H2 is equal to 0.2, and your H3 is equal to 0.35. Now, there are three fluids here. One is water, so this is the water. Then it is separated by oil, and then I have your regular manometric fluid, that is your method. So we have three fluids, and maybe I can start with my data. So this is how usually we try to do it when we are teaching the manometric problem. What we try to do? We try to get the datum between 1 and your 2. Now look at this. What's happening here? At the pipe or the manometer is open to atmosphere. What is the pressure that's acting here? It is your atmospheric pressure. Okay. So a lot of questions will be in your mind. What will happen? Say the same manometer. Now the manometer which is going to give for this particular height, what is the value it is going to give in Bangalore? So now suppose the same thing manometer, if I try to take it to maybe an hill station like Nandi Hills or Tirupati, if I try to do, whether the numbers are going to change? Yes, it's going to change, because this altitude is one particular parameter. Okay, based upon that, my pressure is going to change. Now, instead of, say I have a differential manometer, so what I will do actually, I am going to, this particular, wherever the atmospheric pressure is there, I am going to connect it to the second point. So then, using the same principle, I can measure the pressure or difference in the pressure between two water tanks or two different fluids flowing between the water. Now if I try to write the balance equation or pressure equation, if I call the pressure at point as P1 actually, if I call the pressure at point as P1, then I have rho of density of water, that is rho GH, rho into G into your H1. So if I want, I can write rho of H2 as rho 1. I can write it. So that the first fluid is my water, the second fluid is oil, rho into G into H1 plus C. I'm trying to see, look at this particular thing. What I'm trying to do actually, I'm trying to go up. See, when I'm trying to go up, I'm taking it as positive. When I'm trying to come down, I'm taking it as negative. So that particular rule, it applies here. Fine. So rho 1 G and H1, then oil is, so rho of oil is equal to rho 2, which we can define, rho 2 into G into H2. Then I'm trying to come down. Or you can take it to the right hand side, you can take P atmospheric or P2, whatever it may be, plus your rho of rho 3 into G into H3, or you can write here itself, that is rho 3 into G into H3, and which should be equated to your atmospheric pressure as you have to balance. So what I'm supposed to find here? So in this problem statement, we need to find the pressure in that particular tank actually. So I can write it as the equation will be something like this. So P1 is equal to your P atmospheric plus rho 3 into G into H3 minus rho 1 into G1 into H1 minus rho 2 into G into H2. So this will be my equation. If you want, you can take, when you're writing the program, you can take P1 is equal to P atmospheric plus, I can take my G outside, or I can take rho 3 into H3 minus rho 1 into H1 minus rho 2 into H2. So this will be my problem statement. Or you have the formula. So now, depending after, see, your program should be such that you have to input rho 1, rho 2, rho 3, or you can inbuilt, or you can type in the program. It's a simple column, or you can input it. At the same time, I have to input H1, H2, H3, and I should input my atmospheric pressure. Or you have some kind of a data where you have a curve or something where you can read the atmospheric pressure depending upon the altitude. So that also people can do. So here in this particular problem, already the P atmosphere is given. I can give this as the input. So once everything is, so G is to be defined. So once you have defined all these things, you can calculate the P1 and get the display. Suppose if you have the differential manometer. So what should I do? Instead of P atmospheric, so this will become P. So where you have the pressure at another condition. So that condition you have, and you will equate it and you can get it. So in that case, what you have to do? So for a differential manometer, so I'll be calculating P1 minus P2, and you can write all the things whatever you have, that is G into rho 3 into H3 minus rho 1 into H1 minus rho 2 into H2. So this will be your differential manometer or inverted differential manometer, whatever it may be. This particular values are going to change. When you are going up, you take it as positive. When you are coming down, you take it as negative with respect to your datum. So whatever may be your datum with respect to your datum. So this will be my datum with respect to that. You take the values. So let me show the code what I've written. So I've written the code. So this is the values for the oil. This is the values for the water. These are the values for the mercury. So then I have input the atmospheric pressure and G and trying to calculate your. So look at this. I'm trying to convert the pressure from pascals to kilopascal. That's why I'm dividing it by 1000. Because I have my atmospheric pressure in kilopascals, I'm trying to divide the whole thing by 1000. I can get it. Now, depending upon the round and all, rounding all those things, I will discuss when I try to run the code. So this is about your fluid. See, fluid static problems are most of the times what we look into is either it's with respect to your Pascal's law. So P is equal to omega 2. If you want, you can take up the center of pressure problems or other kind of problems where the fluid is stationary. The one thing is actually here, you should be able to input the what is the values, and you should be able to output equation written and try to calculate fluid. So velocity, acceleration. What is velocity? It's a vector. So velocity is a vector. So V is equal to, or I can write V is equal to your dx by dt. Velocity vector. The vector is nothing but it has both magnitude and direction. See, when we speak of velocity vector, this is three-dimensional. Three-dimensional. It has components. That is, V will have a component that is U, V, and W. Fine. U, V, W. Or if it is three-dimensional, if it is a two-dimensional, I will be having U and V. I can define the value of U. See, U is equal to some 0.5 plus 0.7x. Or I can define V as 1.5 minus some 1.21. So I can define this particular. So depending upon this particular U and V, the whole velocity, I can define the whole vector set. That's one kind of problem where your streamlines, streaklines, I want to define it. What will happen over there? So now when you come to the acceleration, so it is du by dt. That is in the x direction. So there you have the first, which is the substantial acceleration, or your material or local acceleration, what we call it as local acceleration or substantial acceleration. You have the first component, this is your local component. You have the convective component. The second part is my convective component. This is already, we know it, and the same thing can be written in your vector notations also. So based upon this particular problem, so we can define one problem. Say for example, most of us, I think we know that we have a nozzle, and what is the so is you want to washing its car or whatever it may be using a nozzle as shown in the figure. The nozzle, see here, the length of the nozzle, okay, it is the length 1 meter, the length of the nozzle, its inlet diameter and the exit diameter, and what is the discharge. So using this components, I can find what is the acceleration of the fluid. I can easily find what is the acceleration of the fluid. Okay. Now if I want to find the acceleration, I should know whether it is in x direction or y direction, whatever it is. So just now we saw the equation for the acceleration. Say for example in x direction, we have the local component, which is dou u by dou t plus u into dou u by dou y plus v into dou u by dou y plus w into dou u by dou z. Okay. Now this particular problem statement is the steady flow problem. So this component is 0, or it is steady flow component. Then there is no velocity component in the 0, because velocity in 0 along the center line, and I don't have the third component in the order. So what will happen? I'm going to have actually your a of x is equal to, or your acceleration is equal to u into dou u by dou x. Okay. Now what is this u? So this is actually your average velocity. So this velocity, acceleration velocity, suppose I have this inlet and I have the outlet. So if I try to calculate the velocity at the inlet, that is I can call it as U1. The velocity at the exit or outlet, I call it as U out or whatever it may be. Now U average will be average of U in plus U out divided by 2. So this will be the thing. So now if I try to calculate, see what is this particular thing? Delta x, see that is the length of the nozzle. So your delta x is the linear length of the nozzle. What is delta U? Delta U is equal to your U out minus U in. So once I know all those things, I can refine my acceleration formula like this. This will be U in plus U out divided by 2 into U out minus U in by delta x. Okay, this is A plus B into A minus B. I can write it as A square minus B square. So whatever it may be. So in whatever it may be, I can write it as U out minus U in, U out plus U in also. Whatever I want, I can write it. So this equation automatically it becomes U out square minus U in square by 2 into delta x. So now in this particular problem, I can calculate the discharge. How to calculate the discharge? We know that from the continuity equation, your discharge is equal to, for a incompressible steady fluid, I have A into your V or whatever it may be, velocity. So here I can calculate U in is equal to Q by A in, and U out is equal to your discharge by area at the outlet. So U in is calculated, U out is calculated. So delta x is given. If I know the nozzle, I can easily calculate the acceleration of the fluid. Okay. So it's a simple problem what I have taken. So I have written a simple code. So I'm trying to define the length of the nozzle, or either you can input or you can type it over there itself. You have the input diameter, output diameter, the discharge. Then I am trying to calculate the inlet velocity, outlet velocity, and acceleration. I am trying to get the display of all the both the velocity components and acceleration. So simple problem. We can give such problems to the students and we can check. So what will happen if the outlet diameter is varied, if my inlet diameter is varied? What will happen if my discharge is varied? So I say I am giving a very low value, 5.3, 10. So all those things we can have, or we can know what is the varying parameter, what is, or if you can take it further, we can optimize, say what particular value of your discharge, maybe your nozzle has accelerated, has reached the peak. So lot many things can be done. So that depends on how we try to code it, or to be very simple, to make it very simple, I've written like this. So this is a simple code. So this is about your fluid statics, a simple problem, and a fluid kinematics I've taken a simple problem. So now the next part what I'm going to do is actually, most of us, I think we have this particular problem, how we can draw the pathline, streamline, streakline and all. So this will be a bit complicated. Before I could move to the problem statement, I will discuss on the fundamentals of it. Fundamentals is so important for us. See, visual examination of any flow field means where the fluid is flowing. Okay. Now, what is a path? Actually, path line or something. Say, I have a fluid particle at a time start, that is start, let it be t 0 seconds or 1 second, whatever it may be. Then the same fluid particle at some other time point t is equal to 10 seconds. Okay. It's going to trace. See, I can see this is the path it's going to trace. Okay. And I can see really the particles, how it is flowing. So the path traced by this particular thing. So the Lagrangian kind of approach is based on your fluid particle tracking. So, but most of the fluid mechanics problem what we deal with is on Eulerian approach, where we take up the whole volume. The whole volume is taken, and the volume is clearly. So we look at the particles. So volume wise, what's happening? We try to analyze it. So maybe if you look at the PIV, how it works. So particle image velocimetry is one experimental technique where it uses this Lagrangian description or Lagrangian approach of your path line. Okay. Now, what is the streamline? See, streamline, usually we come across this particular thing. So streamline is simply, it's an imaginary line. It's an imaginary line. See, you can look at this, all the green, whatever I have, those are the velocity vectors. So now, if I try to draw a local tangent, if I try to draw a tangent to the locally to that particular velocity and try to join them imaginary, so what I'm going to get? So the point is at particular point x comma y. So the same point or that particular thing, it's at some other thing, x plus delta x, y plus delta y or dy, whatever it may be. So now, whatever the tangent, say the red, at any given point, so if I take one velocity vector, so this is my x component and this is my y component. So you have u as the x component and v as the y component. Now, how can I track it? Actually? So why this particular thing is so important for us? So when you look at this, you have a similar triangles. That means if you look at this one and this one. So why this dx by u, dy by u, it came from similar triangles. So dx by u is equal to dy by u. Fine. Now if I want to solve this particular thing, what we try to do? We try to substitute the value of u and substitute the value of v, integrate it and try to get the relationship between your two components. And that particular component at a given function or at a given, so we need some boundary conditions. See, for streamlines, so what we try to give, if you want to, for some x0 or y0, that is the initial condition of x0, y0 is equal to 1, 1, whatever it may be, at a given time point, t is equal to 2 seconds. Then if I want to get the path line, once again, I need the initial conditions and what is the time point. So at this condition, if I put the boundary condition and try to substitute for this u and v and try to get the equation and try to plot it or whatever it may be, we'll be getting a path line and streamlines. Okay. This is about it. Now, what is the stream tube actually? Your closed bundle or something like I have n number of wires. I have 4 to 5 wires and all the wires are parallel. So at inlet and at exit, both are parallel. They should be running parallel. If I try to put it in a conduit or put it close, so what are I going to get actually in a closed form, what we are going to get is called as a stream tube. This stream tube is so important for us. Say for example, I'm going to see the acceleration of the fluid or deceleration of the fluid. The stream tubes clearly visualizes. So what's happening over there? The fluid is entering. Say for example, you see in a basin, what we see actually, the fluid is towards a particular hole. I could clearly see that it is accelerating. So such visualization we can easily make out from your stream tube. Now, before I take up the problem, what is this streak line actually? Say I have a point. This is your, I call it as injection point. I think if you are doing the Reynolds experiment in your laboratory, you have this particular thing. So we have something called as we are going to put a dye. So when I try to put a dye, the red color is one path line. So at different time points, say t is equal to 1 second, t is equal to 2 seconds, t is equal to 3 seconds. Something like, let me explain it like this. So I have a dye here. So from this particular point, I'm going to inject it. Say for example, this will go, this is with respect to t is equal to 0. So from the same point, I have t is equal to 1. So I have one more, t is equal to 2. So I have one more with t is equal to 3. Let us 4.67. Now, if I try to join this 0 endpoints, what I'm going to get is the streak line. What I'm going to get is a streak line. So we can literally see the path. We can literally draw a streak line, path line, all those things using your MATLAB. We can do that. Okay. Study incompressible fluid. Let's be very simple and try to solve this particular thing and write the code and try to understand rather complicated, because the same rule can be applied to all other problems. The only thing is we have to solve the equation for the given boundary condition and try to put it in the code and try to get the desired solutions what we have. I've taken a very simple problem so people can understand. So I have the velocity field. So there is like u is equal to x and v is equal to some minus yt. So t is a variable here. Now, for this condition, what are the things I need to draw? I need to draw the streamline, the streak line, sorry, path line, and then streak line. Path line and streak line. So let us draw these three particular things for the color. Now, if I want to draw a streamline, same rule apply for that also. What are the conditions required for me? For t is equal to 0, I should have some initial condition, that is, let it be some x0, y0. Let me define that as some 1, 1 or maybe 0.5, whatever it may be. What is this actually? Streamline I have to ensure that it passes through this part. So this has to pass through this particular point. I have to ensure that. Now, if I go to the path line, it is at t is equal to 0, where my x0, y0 is equal to 1, 1. So what I'm going to, for this condition, what I'm going to get actually, at that point, at t is equal to 0, what I'm so t is equal to 0 or t is equal to 1 or t is equal to 0, so I'm able to do it actually. What I'm going to get, that I'm going to get a path line. So now, I should ensure that it is in the loop actually. If I want to put it in a particular grid actually, so what should I should maybe in MATLAB what we try to do is actually, or maybe even in a graph also, I need to define a graph actually. So I need to define what is called as a mesh with a reference point. With this is x, this is your y, and I need to define what is my limiting point, maybe some 5 or 10, whatever it may be. I need to define. So before writing the code, I need to ensure this. Now, I have the equation u is equal to x, I have the equation v is equal to minus y into t. Now let's try to get the equations, then we'll try to move to the code actually. Streamline. Let us look at the streamline. So what is the equation for the streamline? Already we have seen it is dx by u is equal to dy by v. Let's substitute for u and v. So this will become dx by your x. This will be dy by your y into t. It goes with a minus. So let us integrate it. Let's integrate it. So what will be the integration of 1 upon x? This will be log of x, that is ln of x is equal to, so here t is as it is, it's a constant, so I'm going to get minus ln of y by t. So this is my equation. Okay, let's maybe if I want to get some kind of an equation for this, this will be plus some constant. So we have a constant, that is c. Okay. So the equation, this will be ln of x plus ln of y by t is equal to constant. Now, what is it? I need to find this constant. So let's put the boundary condition at x0, y0 is equal to 1, 1. That is at t is equal to 0. That is, so put t is equal to 0. At t is equal to 0. You have this particular condition. What I'm going to get actually, I'm going to end up with. So I'm going to end up with your equation will be something like this. a 1, or your y of xt minus 1 is equal to 0, or it may be some function. Let me call it as some function. So let me call it as some function f. Now the moment I make this particular thing function 0, so I should be able to get, see, for this particular thing, I may get one plot. I may get one streamline plot. Fine. Now, see, this particular thing constant is there. No, this is the constant. The logic here in plotting the streamline is, this is a constant actually. Now, if I try to define this constant as some c or z, whatever it may be, and put it in a loop, I'll be getting the set of streamlines. So that's the logic. For all the values of the, see, for all the values of the c, I should be able to plot it. This is one logic of getting a streamline. So you solve the equation and get it in the form of this particular thing, define it with respect to a function, and when that particular function extends 0, whatever is there, this is your equation of your stream, and we can plot it. Now, what about for the path line, and what about for the streak line? We'll do that. Suppose, for example, if I take the same equation, so we have the equation, what is your u? You have your u, which is equal to dx by dt. V is equal to minus dx by dt, that is your x. U is equal to dx by dt. U is equal to your x, and v is equal to minus by t, already we have. So what is your u? U is equal to dx by dt, and v is equal to dy by dt. Let's define that particular thing. So I can write dx by dt is equal to dx. At the same time, I can write dy by dt is equal to minus y. So let's simplify this. Dx by x is equal to dt, and dy by y is equal to minus t into dt. Dx by t into dt. So now let's integrate it. So if I try to integrate this particular thing, so I'm going to get so ln of x plus, so ln of x is equal to, you have the integration of dt is t plus some constant c1. So on the other side, if I try to do, it will be ln of y is equal to, so integration of t will be t square by 2, so t square by 2 plus some other constant c2. Okay. Now let's try to define it. Let's try to find the bound. So c1, let's find it actually at t is equal to t naught, your x is equal to x naught. Fine. So t is equal to t naught, x is equal to x naught, whatever we have. So what I'm going to get now, all this equation simplifies such that so what I'm going to get actually, it is ln of x by x naught, x by x naught. So I'm going to get t minus t naught. Or at this particular condition, what will be my c actually? It will be ln of x naught minus t naught. Okay, I'm going to get that particular. To the right hand side, if I look into it actually, the same condition at t is equal to t naught and y is equal to y naught, I will end up with an equation ln of y by y naught minus t square by 2 minus t naught square by 2. So this is the two equations what I'm going to get. So what are these expressions? So what will be the expression for plotting the particle? What will be the expression for plotting the particle? So if I look into this particular thing, this equation, if I simplify, your x is equal to x naught exponential to the power of t minus t naught, and your y will be equal to y naught into exponential to the power of, if I take half outside, this will be t square minus t naught square. So look at this. These are the two equations what I got. This is the, if I can easily plot the path. Plot the path. That particular. Now, if I want to draw the plot, maybe plot the path line. See, path of the particle. So this is the plot of the particle. That means what is the path? It's what I can see literally. If in MATLAB you can literally see how the particle is traced. That can be visualized if I look at this particular expressions. Now, if I want to draw a path line, that means the starting point of your path and the end point of your path, I can write an equation. That means if I set up an equation in such a way that a function using this particular thing, I can literally draw the path line. So if I want to do that, I'll take this equation. These two equations I'm going to take. That is ln of x by x naught, ln of y by y naught. I'm going to take it. And I'm going to set up a point. What is it actually? What should happen here? This t naught has to become 0. If I'm able to set that particular point, t naught is equal to 0, I'll end up with what is called as the path line. Let's write the equation for that. This is your path line. So ln of x by x naught is equal to t minus t naught. Ln of y by y naught is equal to minus 1 by half into t square minus t naught square at t naught is equal to 0. If I'm able to do the simplify the equation, and whatever the function I'm going to get, if I equate it to 0 or make it 0, whatever the line I'm going to get, that means try to plot it, try to put a contour, whatever it may be, whatever I'm going to get, that is your path line. Okay. So now, if I try to, this particular thing, if I try to put this ln of your t minus t naught is equal to 0 from the first equation, what I'm going to get, it is ln of x by x naught is equal to t. The second equation, what I'm going to get, it is ln of y by y naught is equal to minus of t square. Now, I have the t here. I can substitute for t in this equation. So, ln of y by y naught is equal to minus 1 by 2 into ln of x by x naught whole square. This is the equation. Or I can write it as ln of y by y naught plus half into ln of x by x naught whole square and is equal to some function, some implicit function, whatever it may be. It is some implicit function. And if I am able to tend this particular thing to 0, I can get path line. This particular equation, if I try to set it in your MATLAB code, this particular equation, I can get the corresponding path line. I have to define it actually. Okay. Now the last thing, that's streakline, then we'll go to the codes. Then we'll go to the code. Okay, streakline. What are the streaklines? See, already I explained that is the locus of the particles injected at a given time in a flow field. and whatever may be the time. So you have t is equal to 0, 1, 2, whatever it may be, that person. Now, what you have to do, so if I try to take the equation, already we know that we have this equation, x is equal to x naught into exponent to the power of t minus your t naught, whatever we have. And we have another equation, y is equal to y naught into exponential to the power of 1 by 2 into t square minus t naught square. Fine. Now, in this both the equation, eliminate the injection time. If I'm able to eliminate the injection time, that is T naught. If I'm able to eliminate it, what I'm going to get actually, I'll be getting the corresponding what we call it as a streakline equation. So if I want to do that, what I will do actually, I can go back the original equation, that is log equation, that is ln of x by x naught is equal to t minus t naught on one side, ln of y by y naught is equal to minus 1 by 2 into t square minus t naught square. Now, if I try to look into this particular thing, what is my t naught here? T naught is equal to t minus ln of x by x naught. So I'm going to substitute this particular equation, t naught, in this equation for t naught square. If I substitute, so what I'm going to get, ln of y by y naught is equal to ln of y by y naught is equal to minus 1 by 2 into t square minus this t minus ln of x by x naught whole square. Now if I take this particular thing to the left hand side, this will become, so minus 2 into ln of y by y naught is equal to, I can substitute this as t square, this is a minus b whole square formula, I can get it as a square plus b square minus 2ab. So minus of minus, this will become plus, this will be 2 into t into ln of x by x naught. So minus, so it will become plus into minus, there is ln of x by x naught whole square. Okay. Now this will be the equation what I want, because t square, d square just simply cancel out. So I can get it as minus 2 into ln of y by y naught is equal to, we have 2 into t into ln of x by x naught minus ln of x by x naught whole square. So this will be your equation. Now, if I try to set this to some function, some implicit function, whatever I am doing, some g is equal to 2 into ln of y by y naught minus 2t into ln of x by x naught plus ln of x by x naught whole square. If I do that, and whatever the, if I try to set this particular thing to 0, whatever the line I'm going to get is the streak line. We have to do this particular thing. Any given problem for a given value of u and v, we have to do this exercise to get streamline, your path line and streak line. So I've taken a simple example where u is equal to x and v is equal to minus yt to explain this particular thing. It's a simple problem. Still, it is so much complex. You may feel it's a lot of mathematics involved. You have to integrate it and you have to substitute for that particular as an implicit function. You have to do that. Now, let's look into that particular code what we have. Okay. So let me first explain for the streamline. Look at this particular thing code. What I have defined, I am defining the x and y. See, why this particular thing I have to define? See, this is required to get my grid points. or grid. I need to get the grid size. I need to get the grid size. Fine, I need to get the grid size. Now, as I told that streamline, streakline, and pathline, all those things, indirectly I have the vector plot because what I'm trying to plot when I have the velocity vector, any tangent to that any given locally what we are going to get it actually local what we are going to get it's a streamline. So I can easily create a vector plot also. So we have an function called as QUIVER to plot the vector. Okay. So now I need to define this particular time point. Look at this. See, if this time point is smaller, so t is equal to 0, instead of 0.1, if I keep it as 0.01, I'll get more finer points. Or even your mesh points also, I have kept it as coarse 30, 30. I can go with 100, 100 or 200. So the more the number of mesh points, your finer will be the mesh plot. At the same time, you have your x, maybe your x and y coordinates, what maybe 5 and 5 are defined. I can go with 10 for the x and 2 for the y. So I can all the variables we can do in your program so that whatever the plot I'm going to get, that should be clear. It should be visual. So your streamline, streakline plot is a visual thing, what we are trying to do. So these variables, we can do that. Now, when I'm trying to plot this particular thing, look at this particular thing, I am trying to plot the u component of the velocity, v component of the velocity. When you look at the code, I'm trying to look into this particular thing to get my thing. Now, so usually we have this problem of visualizing it actually. So what is the font I'm using? So we have an option what is called as GCA. That means what we have your local computer visualization. So that particular thing, you can set a font to that. And I can give a font size of 16. Okay. If I tell that if GCA is equal to some number, okay, GCA is a function which is defined in MATLAB. Regularly we use for the plotting or this particular thing. We use it and we set the limit of that particular thing, which gives a particular number. So I'm trying to define the font of 16 or 14. So that may be just sufficient for you to visualize it actually. Now, once I've defined, so X label, Y label, so to ensure that both are of the same font, I define that. Then title I given. So already you learned in the plot actually, this is a vector plot for this particular thing. So what I'm going to see actually, I'll be seeing a vector plot. When I run the code actually, you'll be seeing that. Now, I need to track the particle. See, already we have seen that. What is this actually? This is your y into x square t. So I have that particular thing. You have the particle, you have your particular thing where I need to look into that particle. So you have minus, so if you go back and see that your equation, what we got for the streamline, it was y into x square t. This was the equation what we got. Y into x to the power of t minus 1. So this is the equation what we got. I told that if I try to put y of x t, y or x to the power of t is equal to minus 1, if I define that particular equation, I'll be getting a single streamline. Now, I can define the value of c. So here what I'm trying to do, I'm trying to define 4 streamlines, 0.5, 1, 1.5, 2. Or you can put a for loop. Within the for loop, they can put c is equal to varying from 0.5 in steps of 0.25 till 4. I may get 8 streamlines. So it all depends on how many streamlines you want. So I'll speak on this particular thing. Draw now and pause. So these two things when I'm trying the code, when I'm writing the code, actually, why we need that actually? This pause is very much required because when we are trying to plot a streamline or pathline, whatever it may be, the code will be running continuously. It's like infinite, it becomes a loop. So what we can do, you can pass momentarily for 0.1 or 0.2 or whatever it may be, momentarily I can get my screen paused. So that particular thing I'm trying to use it. Then hold on and hold off to ensure that whatever I try to plot in the previous thing, it's just hold back. So that particular thing I'm trying to use it. If I try to run this particular code, what I'm going to see is a streamline. If I run y of xt, y to the power of xt, I'm getting a single one streamline. And when I run y xt minus c, I'll be getting, depending upon the value of c, I'll be getting the multiple streamlines which are parallel to each other. Okay. Now, what about for the path line? So, for the path tracking, I have a code. Here, till vector plot is the same, because what I'm trying to do is, so your vector plot is the same. Now, to track the particle, so I have to define my initial point. These are the conditions I need to define. At x naught, at t is equal to 0, what I told the condition at t is equal to 0, where x naught, y naught. So this is the conditions. So when I define the conditions, so based upon these conditions, I can write the plot command. So plot command, you can look at this. What is it actually? I told it is the x0 exponential to the power of t minus t naught. This is for the x, and y0 exponential to the power of minus of into t square minus t naught square. So this is two things I'm trying to plot to get the particle tracking. Okay. If you look at this particular thing, if you do it, so it may come with a default color. Okay, so I'm trying to add something, visualizing it. So I'm trying to use O as that particular, so as a circle, filled circle with black color. So marker, this is something to visualizing, that's it, nothing. Even if you try to do without that also, it will give some default thing it want to give. Or I'm trying to add O as the marker with black color. So I'm going to get the path tracking of that particular particle using this. Now for the path line, so what I'm going to do actually, you have the path tracking. So I need to plot that contour. That is this particular equation what we have. So equation was log of y by y0 plus of into log of x by x naught whole square. We have written that equation. So this equations gives your path line. Fine. And here I have to ensure that I am putting x limit and y limit. You can put x limit as 0 to 5, y limit as 0 to 5. So here, see, you can look at this particular thing. I am trying to change the points, your time points. So when I start with point, you always start with a course, 0.1 or 0.2, whatever it may be. So if you try to refine, see, these are the points what we need to work in when I'm trying to run the MATLAB codes. So refinement of this particular thing, limits. So you have to be a bit careful with these three things. You can get a better visualized plots. Okay. So because someone is asking, what is QR? QR is an inbuilt function to plot the vectors or vector plots. Fine. So this is about your path and path line. The last thing is I'm going to discuss on the streak and the streak line or whatever it may be. Then we'll go to run the code. Now, here one extra thing I'm trying to do. So here, many things can be done in your streak lines actually. If you want to add some colors to it, a single track, see, I can, if I try to, whatever the code I have given, so that code will give a single black color, whatever, a black color with this thing. So here also I can add some multicolors to it. That can be done. That also can be done to make it more your streak line or streak particle tracking, more maybe visual effect we can do. So extra thing what I'm trying to do here is actually, okay, for path tracking. Okay, for path tracking, I have this particular equation. Look at this equation. So your x equation and your y equation, what we have. The extra thing what I'm trying to do, I'm trying to add one particle index. That means I want it for, say for example, T0, T1, T2, T3, T4, T5, like that. So I'm going to add that particular thing depending upon. So here 0.2 0.4, 0.6, still I get till the 5. So now, wherever you have the variable t0, it was there I will bring in this particular, because I want to track that particular, wherever it is going. So wherever that particular t0 becomes 0, maybe that particular becomes 0, I need to ensure that it has to get a contour or it has to get a plot using those points. So with that in a condition, I am trying to put it. Now, once you particle index, see, initially I'm going to define it. I need to add it. I need to add. See, what is the next step? Once it is t0 plus 1, so next step. Then next step. So I need to ensure that till this loop executes, this condition has to be ensured. Now here, when you are defining your t and t0, you ensure that both are very similar. Or if you define, see, if this endpoint is 5, this endpoint is 5. If this particular t0, you make it, see, if you, for example, t, you make it as 0.01, that means the code will run slower because I'm trying to refine the point, and this point ensure that this t0 and your t, you are playing with that particular number, it should give a visual effect. With that condition, we have to look into it. So this is about the explanation of the codes and all. So even for the streak line, whatever I told, that is for the particle streak, and we have the same thing. If I try to, same path, streak line, streak path and streak line, we have the code, same code. So where with marker, all those things. So this is your streak line code. This is to the previous code was to line this streak, maybe the streak path actually, what are the points, to look into that particular points. But if you want to draw that particular thing, you have this equation. So this equation is for x and y. This equation, if you want to draw, you're going to get the streak line. And the old equation, you will get the streak line. Now look at this. I have put 0, 0. What is this actually? At the 0 condition. Suppose if I don't put it actually, I'll be getting n number. So I have used the same condition for your streamline as well as for your streak line. If I don't put that actually, it is for first level, 0th level. If I don't put that, it will take for all the levels. So I'll remove that and I'll show you when I try to run the code. I think we have around 15-20 minutes. So this code, this program is to calculate the absolute pressure and the height of the fluid. Now, as I told that I'm going to input the density, height, and G, everything is input, G is already inside the code, and I'm going to calculate the pressure. So let me run this particular code. We enter the value of the density. So maybe in the problem statement it was 1020 or something. Let me give that. And the height was so 1.2 meters, whatever it may be, 1.2. So now let me move this little up. Okay, look at this. I'm getting the absolute pressure as 12 kilopascals and the height of the bottle. So new this thing is 2 meters. Whatever. Now look at this. What I have done is, so the same thing can be displayed. See, look at this. I'm rounding off the, see, you look at this particular code. I'm using this thing, round off to 1 decimal. So you have taken H1 and round off to 1 decimal. So if I round it off to 2 decimals and run the same code, you can see that. So this particular thing, so depending upon your value. So depending upon, see, you the same thing I will use f print to get it to 2 decimals. I can round it off to 1 decimal or 2 decimal, whatever it may be, depending upon that particular value. When I round off, actually, it will be round off whatever. Anyhow, this particular problem directly I'm getting it, it's not an issue. But sometimes if you are using a round, you can round off the number, or you can use this particular command, print command with percentage, maybe 3.2 or 4, whatever the 2 decimals or 3 decimals, you can use that and you can get it. It's a simple code actually. Now going to the manometer fluid. So here once again we have P atmospheric plus rho GL. This I'm not going to take too much of time on this still nozzle, but pathline, streamline, and all I'll take more time. Okay. Now, if I try to run this code, so it tests as input the specific gravity of that particular thing. Let me put it as 0.85 or 0.95, whatever it may be. From atmospheric pressure as local. What is your column of your particular thing? So let me put it as 0.55 or 0.6 meter, whatever it may be. You can see automatically it calculates the absolute pressure. It's a simple thing. Once again, I'm using fprint option and display option. The same thing holds good for your second code, that is other manometer code also, where I have to input the all the three heights of the three fluids as well as the. Okay. So now if I try to run this code, so it asks for what is the height, what is the height of the oil in the H1, that is 0.1, and what is the density of the oil, maybe if I put it as 850, so it is 0.2, and maybe it is water 1000, and it is 0.35, and 13,600 is the mercury. I can give that. And what is the local pressure, atmospheric pressure? It is 85.6 kilopascals. We can see that the absolute pressure is, so I not put the comment in that, so I am getting the absolute pressure is around 125, 9.5. Now for the nozzle problem. The nozzle problem, if you look into that, so let me put CLC. If I try to run this code, so what is the code actually? I am trying to calculate the inlet velocity, outlet velocity, and your acceleration. So that particular formula is there depending upon the nozzle length. So now nozzle length, you can take it as an input the length of the nozzle, input the diameter of the nozzle, input the outlet of the nozzle, or what is the discharge. That also you can make it the input parameter from your problem or from your computer, and you can solve that. Now the real fluid kinematics problem, I will come to it. Streamline. This particular problem was, I told, let me run the code. Okay, if you run the code, see what you are seeing is actually it's running in the loop. You can see I have limited to 4 streamlines. I have limited to 4 streamlines. You can see how this particular condition, it's continuously, it keeps running. It keeps running, and now it has converged. Look at this particular thing. Now if I will try to zoom it. You can see that. You can see that what I could see is actually it is a velocity vector. You can see the velocity factor, this particular thing. What I have done is I have defined a mesh grid, okay, mesh grid of 0 to 5 on the x-axis and 0 to 5 on the y-axis, and within that I have defined the vector, that is your qver. What we have, I have defined no q u i v e r, that gives your velocity vector. Fine. Now once I have that, actually I am going to the streamline plot. The streamline, what I have done is I have taken the contour. Look at this particular contour, where I have an equation yxt minus c I have used. Now instead of that, actually what I am going to do actually, so now I have gone to the for loop. So what I will do is actually I will comment this for loop. I'll comment this for loop and I'll put it as 1. Okay. Now if I try to run this, yeah, you can see it's a single streamline. It's a single streamline. So the single streamline equation is yxt minus 1. So I can get the similar, so depending upon your x and y values, I'll be able to get. So now the plot has converged. So this particular thing, I can make it more smoother. How can I do that? Actually, I can do that if I go here. So I have defined this as maybe some 30. I'll make it some 100. So this I'll make it some 80 or 100. Okay. This also I'll make it some 80 or whatever it may be. Now I'll run the code. It becomes, you can see that it becomes more smoother. So depending upon your velocity or your mesh grid file, what you're going to use, you can clearly define and get your streamline. You can get n number of streamlines. So depending upon whatever may be the equation. So though the procedure remains the same, whatever the procedure what I told, the procedure remains the same. The procedure to get the plot remains the same. So the one thing is actually, first thing is you have to get the vector plot. Vector plot, in that, see, for this particular problem, u is equal to x, v is equal to minus yt. Say I have some other problem where u is equal to 0.2 minus 0.x, so that you have to define. V is equal to some 0.5 minus 0.8t, something is there, so that you have to define. Ensure that all the variables are defined and your u and v is clearly defined to get your that is your vector plot. And x label, y label, you are defining your title and all, so the plotting procedure remains the same. So GCA, just to ensure that it is properly defined, that's it. Either this is an optional, settings that is setting GCA, all those things, it's optional, what font you want. Now, to get the streamline plot for all the conditions, say instead of, say for example, now instead of 1, I'll go for c is equal to, say from 0.5 in steps of 0.10, I'll go up to say 6. So now expect 0.5 to 6, I have to get more number of streamlines. Yeah, once the code starts running, I think I'll run the code. You can see that how many plots. So we have more number of streamlines. Now it's still converged. So it is going step by step, and till the loop is completed, this will be done. So I'm able to visualize this because I put a pause of 0.1. So that's why I'm able to see this particular. So still the loop is running. The loop is running. So I could see that this particular thing. Once the loop completes, I'll be able to see the all set of all the streamlines, they are parallel to this. It's nothing but I'm going to take the equation and I'm going to solve it. Nothing else I'm doing. So the most important thing here is actually you have to solve the equations for streamline, streakline, and pathline and try to get the plot out of it. Okay. Let's go to the path. So this particular thing, if I try to run the code, yeah, you can see the path. I think it's at the bottom. You can see this particular path. It is slowly it's going because I given a step size of very small step size. Maybe I can change this particular 10, 10. If I change it to 5, 5, I think this will become. You can see this particular thing. I can see the particle tracking path. Okay. You can see the path of that particular fluid element, which is very slow because the code I given more number of points. I can change that. Look at this particular thing. Instead of 0.1, I put this particular thing. This also I will change it to 5. This also I will change it to 5. Now you can see this particular thing. You can see it's going fast. What I made it little coarse. That's it. Rather than making it finer, I made it little coarse. I'll rerun the code. You can see that. Okay. So it all depends on the time points what you are taking here. So you may take it as 0.1 or 0.05, whatever it may be. Now you want more finer one. Just I can go here and make this as 100, and this I'll make it 2. Okay, this I'll make it 100. It's 300. It's also make it 2. Make it 10. You can see this. It will be a bigger one. Yeah, you can see the path. I can wherever I want. I can, depending upon the mesh particular thing, I can see this is the tracking of the path of that particular fluid element. I can do that. Now I can, if I try to order the equation, whatever that equation, I can, wherever this particular path is taking, I can draw a line. So that is what I have the next code. Next code, that is This is the thing. If I try to run this code, you can see this. You can see that. So that is the line. So I can still refine it. So I can refine. So you can see that the path, that is the path, and the corresponding path line. It's clearly tracking what's happening. So the more the number of points what you can see this particular, you can see the visual effect of this particular tracking of this particular path. You can see that how it's going. So this is about your path of the particular particle and tracking of that particular path, drawing a path line. I can do it. Maybe the last one. First I will show the streak point, then I will show the streak line, how to draw the streak line. Now look at this. This is a streak line, a streak point actually. That means injection points. From the injection point, how the points. So I can give a color code for this. Say for example, I can give some string colors of 4 to 5 colors, maybe red, blue, green, cyan, and all. If I do that, each point what you are seeing as a black, I can change it to different colors. That also possibility is there. Now, same thing, I can get a path, that is streak line actually. What I'm trying to do for the streak line in this code, if you look at it actually, the changes what I have done is, I have done it. So this T0 and T ensure that they are of the same thing. Okay. Otherwise, they will tell that it's out of the particle. And here, this code, it was T0. I made it with respect to put it in a loop, depending upon your particle index, 1, 2. And then I'm trying to put a contour for the equation which we derived at the last. And you see, this is at the 0 level. Even for the streamline, if you look at it, it was a 0 level. It was at 0 level if I'm going to look into it. Now, if I try to run this code, yeah. First, I'm trying to get all the streak line points. Then I'm trying to get the path. Still, this path you can refine it depending upon your points. Say, for example, now I have some 30 points. I can make it 300. This I can make it some 100. So this will become. You can see that it's become smooth. Now you can see this becomes smooth. Yeah, you can see that. So it all depends on how coarse you keep your mesh grid and how fine you keep your mesh grids to get the desired output. The path line, streamline, streak line. So I think that's it from my end. So